Polymers with high thermal conductivity. Thermal transport mechanisms, bottom-up synthesis, and emerging thermal management applications. Polymers have traditionally been regarded as thermal insulators, exhibiting thermal conductivities of only 0.1 to 0.5 watts per meter Kelvin due to their disordered molecular structures, weak intermolecular interactions, and extensive phonon scattering. Although advantageous for thermal insulation, this limitation has become increasingly critical in high-power electronics, electric vehicles, flexible devices, aerospace systems, and wearable technologies, where efficient heat dissipation is essential. Consequently, the development of intrinsically thermally conductive polymers has emerged as a major research focus, offering lightweight, electrically insulating, corrosion-resistant, and mechanically flexible alternatives to conventional metallic heat spreaders. Recent advances in polymer chemistry have fundamentally challenged the traditional view that polymers are inherently poor thermal conductors. Both theoretical and experimental studies demonstrate that thermal transport is governed primarily by molecular architecture rather than chemical composition. Molecular dynamics simulations predict that highly aligned polyethylene and conjugated polymer chains can achieve thermal conductivities exceeding 100 watts per meter Kelvin under ideal conditions, while experimental studies on aligned polyethylene nanofibers, conjugated polymers, ladder polymers, and molecularly engineered thermosets have confirmed substantial enhancements in thermal conductivity. These discoveries have established molecular design and chain organization as key strategies for developing high-performance thermally conductive polymers for advanced thermal management applications. Fundamentals of thermal transport in polymers. Unlike metals, where electrons dominate heat conduction, according to the Wiedemann-Franz law, heat transport in polymers is governed almost entirely by atomic vibrations known as phonons. In crystalline solids, phonons propagate coherently through periodic lattices, enabling efficient energy transfer over relatively long distances. However, polymers differ fundamentally because their molecular structures often lack long-range periodicity. In semicrystalline and amorphous polymers, phonon propagation is disrupted by numerous scattering centers, including chain entanglements, crystal amorphous interfaces, molecular defects, impurities, chain ends, voids, conformational disorder, and random coil structures. These structural imperfections drastically shorten phonon mean free paths and consequently reduce thermal conductivity. For highly disordered polymers, the conventional phonon gas model becomes insufficient because phonons are no longer well defined. Instead, heat transport is increasingly described using the Allen-Feldman framework, which categorizes vibrational modes into propagons, diffusons, and locons. Propagons behave similarly to conventional phonons. Diffusons transport heat through diffusive vibrational hopping, while locons remain spatially localized and contribute minimally to thermal conduction. Understanding the relative contributions of these vibrational modes remains an active area of theoretical research and is central to designing polymers with enhanced thermal transport. Molecular design principles for high thermal conductivity. Modern polymer chemistry has shifted from relying on thermally conductive fillers toward engineering intrinsically conductive polymer backbones. Several molecular parameters have emerged as dominant factors governing thermal conductivity: molecular chain alignment, crystallinity, backbone rigidity, molecular weight, chain orientation, intermolecular interactions, copolymer sequence, cross-link architecture, defect density, chain packing, conformational order. Highly aligned polymer chains substantially reduce phonon scattering by creating continuous pathways for vibrational energy transport. Similarly, increasing crystallinity extends phonon mean-free paths, although crystallinity alone does not guarantee high thermal conductivity, as demonstrated by crystalline polypropylene, whose flexible backbone limits heat transport. Rigid conjugated polymers such as polyacetylene, polyphenylene, ladder polymers, and polythiophene suppress torsional motion and segmental rotations, thereby reducing anharmonic phonon scattering. Furthermore, stronger intermolecular interactions, including hydrogen bonding and pi-pi stacking, provide additional pathways for interchain heat transfer that are absent in conventional van der Waals-bound polymers. Bottom-up atomic-level synthesis of thermally conductive polymers. Rather than modifying existing polymers through fillers, bottom-up approaches construct polymer architectures with thermal transport engineered directly into the molecular framework. Oxidative chemical vapor deposition. Oxidative chemical vapor deposition enables atomically controlled polymerization of conjugated polymers while simultaneously improving chain ordering and intermolecular packing. Poly-3-hexylthiophene. Thin films synthesized by this method exhibit thermal conductivities nearly 10 times higher than conventional solution-processed films due to enhanced pi-pi interactions and improved molecular ordering. Template-assisted electropolymerization. Anodic aluminum oxide templates guide polymer growth inside nanoscale pores, producing highly aligned nanofibers. Template-grown polythiophene nanofibers have demonstrated thermal conductivities approaching 4.4 watts per meter Kelvin, representing more than a 20-fold improvement over bulk material despite remaining largely amorphous. Chain orientation rather than crystallinity appears to dominate thermal transport in these systems. Surface-initiated polymerization. Surface-initiated controlled radical polymerization produces densely grafted polymer brushes with excellent chain alignment. These vertically oriented architectures minimize interfacial resistance and improve through-plane heat transport, making them particularly attractive for thermal interface materials in microelectronics. Molecular engineering of thermosets. Epoxy resins remain among the most widely used thermal interface materials. Rational selection of aromatic monomers, rigid hardeners, and optimized cross-link densities has demonstrated measurable improvements in intrinsic thermal conductivity. Aromatic and naphthalene-containing curing agents generally outperform aliphatic analogues because of their greater molecular rigidity and enhanced vibrational coupling. Hydrogen-bonded and ampholytic polymers. Hydrogen bonding provides significantly stronger intermolecular coupling than van der Waals interactions. Ampholytic polymers exploit extensive hydrogen bond networks to facilitate heat transfer between adjacent chains. Studies further indicate that hydration may enhance thermal conductivity through formation of water-mediated transport pathways. Rational copolymer design. Copolymerization enables simultaneous control over rigidity, free volume, chain extension, and intermolecular packing. Pentiptysene-based poly-O-hydroxyamide. Copolymers demonstrate that increasing rigid aromatic content enhances chain extension while reducing free volume, thereby improving thermal conductivity and producing pronounced anisotropic heat transport. Characterization of thermally conductive polymers. Reliable thermal characterization is essential for correlating molecular structure with heat transport behavior. Steady-state methods determine thermal conductivity directly from Fourier's law after thermal equilibrium is established and remain useful for bulk polymers. Transient methods have become increasingly important because they permit rapid, highly accurate measurements over broad temperature ranges. Laser flash analysis, LFA, remains the industrial standard for determining thermal diffusivity of polymers, composites, ceramics, and thin films, from which thermal conductivity is calculated using measured density and heat capacity. Time-domain thermoreflectance, TDTR, has become indispensable for nanoscale polymer films because it provides directional thermal conductivity with sub-micrometer spatial resolution. Scanning thermal microscopy, STHM, further enables nanoscale mapping of local thermal conductivity, revealing spatial heterogeneity arising from crystallinity, interfaces, and molecular orientation. Together with molecular dynamics, simulations, and first principles calculations, these techniques provide increasingly detailed insight into structure-property relationships. Emerging applications in thermal management. Highly thermally conductive polymers are poised to transform numerous technologies. Electrically insulating yet thermally conductive polymers are attractive for electronic packaging, power electronics, batteries, and semiconductor devices, where they dissipate heat without creating electrical short circuits. Their low density and corrosion resistance make them promising replacements for metallic heat exchangers in aerospace and automotive systems. Flexible polymeric heat spreaders are also being developed for wearable electronics, biomedical devices, and soft robotics. Additional opportunities include thermally conductive fibers for smart textiles, organic light-emitting diode displays, and advanced thermal interface materials for artificial intelligence hardware and data centers. Future perspectives. Despite significant advances, major challenges remain before thermally conductive polymers achieve widespread engineering applications. Experimental thermal conductivities remain well below theoretical limits, highlighting the need for a deeper understanding of phonon transport, enharmonicity, and interchain interactions through integrated multiscale modeling and advanced characterization. Future research will emphasize molecular-level design of rigid polymer architectures, sequence-controlled polymers, covalent organic frameworks, and supramolecular systems, supported by scalable synthesis methods that preserve chain alignment and crystallinity. Standardized techniques for accurately measuring anisotropic thermal conductivity are also essential. Continued progress in bottom-up molecular engineering is expected to enable intrinsically thermally conductive polymers with lightweight, electrically insulating, and mechanically flexible characteristics, making them key materials for thermal management in advanced electronics, renewable energy, aerospace, and wearable technologies.